Hey everyone, welcome back, and thanks again for attending another video session in this series on predictive analytics. I wanted to put together a notebook and corresponding discussion on model classes. So we're going to look at a bunch of different model classes for regression, so linear regression, tree-based regression, k-nearest neighbors regressors, and there are lots of others. And also for classification, so there are k-nearest neighbors classifiers, there are tree-based classifiers, there's logistic regression as a classifier. So lots of different model classes, and I think it's worth taking a look at what those model classes are, what types of data they're well suited to, and how they perform differently than one another on a toy data set. In particular, if you're coming to this video off of the bias variance trade-off video in Notebook, there you were exposed to linear and curvy linear regression models. We took a single numerical predictor to try to predict a numerical response. We saw that we were able to make our models very, very flexible, very wiggly, but that didn't always translate into better model performance. So like I said, in this notebook and video, we're going to look at different model classes beyond just linear regression. Okay, so we'll start out with regression models, and we will start out with linear regression. What I'm going to do is build a toy data set. So hopefully you're starting to get familiar with some of the things we're doing at the beginning of these notebooks. I'm going to import a couple of libraries. NumPy allows us to do some random number generation and mathematical operations. Pandas allows us to work with data frames. Data frames are kind of a central object for us. They're what houses our data. They're like a single tab Excel spreadsheet or a CSV file. We're going to import matplotlib.pyplot. This is a plotting functionality, and I'm importing Seaborn here, which is also extended plotting functionality, even though we're not going to end up using it. Now I'm going to generate some random X values. These come from a uniform distribution. So essentially here, all values are equally likely. We're going from a low of 0 to a high of 100. So anything possible in that interval. And we're going to grab 15 of these X values. Then we're going to create related Y values. Those Y values are going to be related here by a linear function, 3 times whatever the X value is plus 12. But then as usual, we're going to add noise to this relationship. The noise we're adding is going to have a standard deviation here of 40. As a reminder, we've mentioned this before, but the larger that standard deviation, the more each observation can on average deviate from this linear relationship. So the bigger that number is, in some sense, the harder the regression problem becomes. Then we're going to take that data X and Y and just collect it into a data frame so that this will look like a table. We'll print out the data frame and let's look at a scatter plot of the data we're working with. Again, this data doesn't mean anything. It's random data generated by the computer. And so here's the data that we're going to work with. We're going to try to model this. So we're going to try to predict Y as some sort of a function of X. Again, we'll start with linear regression. We're going to start with just a basic straight line linear regression. And this is new for us. We're going to import from sklearn, a model object. sklearn, also called scikit-learn, is probably the most popular machine learning library on the planet. It's the machine learning library that we're going to use from basically from here on out. So almost everything we do will be from scikit-learn. And there's a real nice reason for that, and that's because as soon as you know how to build a linear regression model with scikit-learn, we create an instance of it, then we fit it. You know how to build any other model class that you might want to build. So all of the modeling here is really standardized. So what we're going to do is create an instance of this linear regression model constructor. Then we're going to fit that model to our data. So we're going to allow access to the inputs or the predictors X, and we're going to try to predict the response column, which is Y. Then we're going to create some new data. Basically, we're doing this just to plot. So I'm creating some new X values. I'm using NumPy's linspace function to create a linear space between 0 and 1. This is just going to create a bunch of kind of equally spaced values along that interval. It's going to allow us to do some prediction and plotting. Then we'll build straight line predictions. So these are predictions coming out of our straight line regressor. So nice things about scikit-learn, once we have a model constructor and we fit that modeling object, we can use its predict method on some new data to make predictions. We've just got to make sure that the new data that we feed the model looks exactly like the data that the model was trained on. Here's what we mean by that. We just mean that it has the same columns. So the model was trained on a data frame whose only column was X. We're asking for predictions using a data frame whose only column is X. So this will work just fine. Then we're going to build a scatter plot. So we're going to plot the original data. Just to be consistent, I'm going to do data X and then data Y. This will plot an X coordinate here, which is equal to the X values we generated, and then the Y coordinate. And then on top of this, we're going to plot our regression model. So this is the new data, that linear space that we generated, along with the model predictions colored in red. Okay, so the blue points are the original data that we generated, and the red line is the optimal linear regression model. Okay, so now let's, for the fun of it, build a curvy linear regression model, something that's allowed to bend a little bit. So we'll add an X squared column to the data frame to allow for curvature. So here's where we're doing that. We're saying go to the data frame and look at the column called X2. We don't have one of those, so we're going to create it. That's equal to, well, whatever I see in the X column, and I'm going to square it. So in Python, we can't use the caret operator. Exponents are a double asterisk. So **2 is squaring that column. Now we'll define a new linear regression object. I'm just going to call this one curvy reg to remind us that this one's going to have a curve associated with it. That curve, again, is because we have this X squared column. We're going to fit that linear regression object, but now we're going to allow access to two columns of predictor variables, the original X and the X2 column, which is X squared. And we're going to try to predict the response Y. Again, we're creating new data to make predictions on. In that new data, we need to have access to all of the columns that the model was fit on. So our new data is going to have an X and an X squared column. And so that's what we're doing here. And then we'll make predictions on that new data frame and we'll plot again. So I'm just going to leave this as X and Y. It's fine. It's just pulling the original X and Y we created before putting them into the data frame. And then on top of that, we'll plot the new data, the curvy linear models predictions, and we'll plot that in green. And so we see that this model was allowed to bend a little bit. We can see both models one on top of the other and compare them. So the plotting functionality in matplotlib is really pretty nice. We can just add layers to a plot with successive calls to PLT and plot sort of geometries. So a scatter plot or a line plot. So here we're going to have the original X and Y data. We'll have the straight line linear regressor we built plotted in red, and then the curvy linear regression model in green. Perfect. And so we can see that the two models perform differently than one another. We haven't really talked about model assessment yet, so we're going to leave that alone. But here are linear regression models. This is a particular model class. You'll notice that linear regression models don't actually have to be straight lines. So we're allowed to embed curvature in our model. And the way we do that is just by adding columns corresponding to higher order terms or higher order functions of variables. Okay, but let's move beyond linear regression and let's look at something called a tree-based model. Tree-based models are going to make different assumptions about the underlying structure of our data. Basically, we can ask questions about the predictors, yes or no questions, and the answers to those yes or no questions will be informative as to predicting a response. And so what we're going to get here is not this sort of smooth, continuous function like we had in linear regression. We're going to see a function that's broken up into a series of steps up or down. Tree-based models are really nice because they mimic our own decision making in an if this, then that sort of manner. And trees are really easily understood without any technical background at all. Everybody has seen a decision tree before. Okay, so nice things. We're going to import the decision tree regressor from scikit-learn. We just have to go to a kind of a submodule here. So sklearn.tree contains tree-based models. And the decision tree regressor is the object that we're going to be working with now, or the model class we're going to be working with. And then plot_tree is just some functionality that allows us to draw a picture of the tree that results from a fitting process. You'll notice that the way we build a decision tree is the same as the way we built a linear regressor. We're going to create an instance of this decision tree regressor object in tree_reg. Then we're going to fit that object on our training data. We're back now to just having the single predictor X and the response Y. So we'll fit this model and then we'll plot the decision tree just so that we can see kind of what it looks like. And so this, we can't read it very well. I'm going to blow this up a little bit and see if we can read the text there at all. Okay, so I think you'll be able to see this, but the way these work, and we'll talk about them later in our course, is all of the observations start out in just one giant bucket. And if all of the observations were in one bucket, we would just predict a single response for everything. That single response would be 188.682. But if we're allowed to ask a question before making a prediction, then what the decision tree regressor functionality has done is it's gone through and tried to ask an optimal question. And so the optimal question that it decided on was, hey, is the value of X less than or equal to 30? Yes or no? So yes answers will always move off to the left in these trees. No answers will move off to the right. And then we can see, oh, we have two buckets now and two separate predictions. But if we're allowed to ask more questions, then we can go deeper down into this tree. And so you can see that the tree structure does kind of mimic our own decision making with this if this, then that structure. You can see some grayed out boxes down here. This just means that the model would like to continue asking questions, and it has continued to ask questions. We're just not plotting the bottom of that tree. And so let's take a look at what this model actually looks like. So we're going to use this tree-based model that we built, tree_reg. It has a predict method just like the linear regressors did, and we're going to feed our new data to that predict method. We've already created new data earlier, so we're just recycling that. We're going to store these predictions in this object called tree_reg_preds. Then we'll plot the original data, and we'll plot our model's predictions. This time they'll show up in purple. And so we can see this model is a step function. It's moving up and down. These flat line regions correspond to buckets at the bottom of our tree where our tree is happy and making predictions. You'll see that this tree fits the training data really well. But again, if you're coming off the bias variance trade-off video, this model is really flexible. It's very wiggly. It fits all of the training data points almost exactly, and that's a high risk of overfitting. So the idea here is that if one of these training data points moved, we would get a model that looks quite different. So this model is high variance. It's really highly sensitive to the training data that we have access to. This is a shortcoming of trees in general, actually. Trees are prone to overfitting. They're really enticed to get as close to the observations as they can. Because of that, we have some controls with trees. So we can control the flexibility through a bunch of different characteristics. We'll talk about those characteristics later in our course when we get to tree-based models. But for now, one of the simplest controls to think of is the maximum depth argument. So this just controls how many questions we're allowed to ask in constructing a decision tree. It'll control how many layers the tree has. So let's control the layers in our decision tree. We're going to force a maximum depth equal to 2. So once you've asked 2 questions down any given branch, you have to stop with this tree. So again, we're creating an instance of a tree. We're not accepting all of the default values for our decision tree regressor. Here we're overriding one of them. We're saying the maximum depth should be set to 2. Once we've done that, we're going to fit our tree on our training data, just like before, nothing changes. And now we're going to plot our tree. And so you can see that along each branch, we've asked at most 2 questions before ending up in a prediction bucket now. And let's see how our decision trees compare now. So we'll create predictions from this new constrained tree. We'll plot our original data. Then we'll plot the the first tree we made, so the unconstrained tree, and then we'll plot the constrained tree's predictions in black. And so we can see that the purple decision tree resulted in a very, very flexible model. It's almost surely overfit. And the black decision tree is less flexible. It's less likely that it's overfit, but still you have a step function rather than a smooth curve. Okay, so let's take a look at all of our models so far. We're going to do this in a single plot, and later on, we'll kind of break these apart and look at kind of a gallery of the models that we've constructed so far. So the original straight line linear regression model is in red. We allowed some curvature in a linear regression model here in green by allowing the model access to a squared column for our predictor that we called it x squared. We had this really flexible, very deep decision tree regressor in purple, and then we constrained it using a maximum depth constraint to arrive at the black model. And so you see that the trees are step functions, like we said, while the linear regression models are smooth curved functions. Let's move on to another class of model for regression. So support vector regressors were very, very popular for a while, and they perform really, really well. It seems to me like they're becoming less popular as new methods are kind of taking over, but they're worth looking at. Support vector regressors and support vector classifiers, we'll see later on, are models that are distance-based. So they really rely on an ability to compute distance between observations. And a real drawback to this is that categorical predictors are not well suited to these models because we have no great way of defining a distance between red and blue. There's a lot of guesswork kind of in there. Unless we have some real domain expertise that we can justify defining a distance metric there, or defining an encoding of red or blue where distance is meaningful. Okay, but let's get back to the model building. So again, we're going to import our model class. So the support vector regressor lives in the sklearn.svm, that's support vector machine submodule. We're going to create an instance of our model. We're overriding a default setting here by setting the kernel to linear. So that's something that kind of governs the linear algebra behind this model. We're not going to get into it because this is a business course. But if you're interested in the mathematics, come talk to me. Once we have that model instantiated, we're going to fit it to our data. So we have the predictor column X, and then we have the response column Y. We'll create our predictions. Again, this is the same as what we did before. We have the support vector regressor object that we just fit. Once it's fit, it has a predict method that we can use, and we can predict on new data. The only trick is the new data has to look exactly like the data that the model was trained on, meaning that it has to have the same columns. So we need an X column here, which it has. We're going to plot the original data, the X and Ys, and we'll plot then our model's predictions on the new data. And so here we are. Looks a lot like our first linear regression model, which is not a surprise because our support vector regressor is producing a linear model to make predictions here. So let's see actually how our original straight line regressor and the support vector regressor compare. You see that they're nearly identical here. They have slightly different slopes. And if we generate new data, we may observe more or less difference between the two model classes. But here they pretty closely agree. All right. And before we move on to classification, let's look at one last class of regression model, this one called k-nearest neighbors. This one is also a distance-based model, which unfortunately means it's not well suited to categorical predictors. But the assumption made by k-nearest neighbors is that observations should be most like the observations that are closest to them. So what a k-nearest neighbors model will do to make a prediction on a new observation is it will look at its training data and identify the neighbors which are closest to the new observation. Then it'll take those the response values from those closest observations and aggregate them together to make a prediction. So an aggregation might be taking the mean of all of the responses for those near neighbors, or the median, or another metric that we can define. We also get to define how many close neighbors the model is going to look at in making predictions. And that's actually going to determine a lot about the flexibility of the model. Remember, flexibility is related to bias and variance and overfitting and underfitting. So again, we're going to import the model class. K-neighbors regressor comes from the neighbors submodule in scikit-learn. We're going to create an instance of our model. We're going to set the number of neighbors to look at to 3 here. And then we're going to fit our model to our data. So the only predictor it has access to is X, and the response we're trying to predict is Y. Once we have fit that model, we have access to the predict method for it, and we can make predictions on new data. So we're just carrying this new data the entire way through this first part of the notebook. This was the linear space generated from 0 to 100, so equally spaced observations in that interval. So we're making predictions from this model. Given those new X values, this is going to allow us to draw a model. We're going to produce a scatter plot of the original data, followed by our model and its predictions in red. And so we can see that the k-nearest neighbors model looks a little bit like our decision tree regressor. It's more of like a step function. And so, yeah, it's in this application, it looks like it's kind of a little bit between our straight line linear regression model or a curvy linear regression model and a decision tree model. So like we said here, we were allowed to set the number of neighbors that the model looked at when making predictions. The model and its predictions are really sensitive to this value, and we have to be careful how we choose it. So I'm going to look at an extreme case and then kind of a more conservative case. So we'll build two new models, one that looks at just a single nearest neighbor when making predictions, and then one that looks at 7 nearest neighbors when making predictions. In this high variance k nearest neighbors model that looks at only a single nearest neighbor when making predictions, that one neighbor has full influence over the model's predictions. This is going to be really, really sensitive to the training data that we have access to. In the lower variance model, where we're looking at 7 nearest neighbors, well, now the influence is fractured across 7 close by points. And so each individual data point, each individual training observation has less power and less influence over the ultimate prediction. And so this model is going to be less flexible, more biased. It's going to be closer to kind of a straighter line prediction. And so we'll take these new models that we fit and we'll generate predictions with them. So here's the original k nearest neighbors model with 3 nearest neighbors. Here's the high variance model with which looks at a single nearest neighbor, and then the low variance model that looks at 7 nearest neighbors. We're getting predictions from all of those models. And then we're going to create a plot. Here we're going to produce 3 separate plots side by side to make things a little bit more readable. And so we can see in green, with a high variance model looking at a single nearest neighbor, this is a very, very flexible model that's really dependent on the training data. It's responding to all of those training data points, and it's really highly likely that this model is overfit to that training data. When we try to apply it to new data, it's probably not going to fit the new data, definitely not as well as it fits the training data. Here in red, we've got kind of a middle ground that looks at 3 nearest neighbors. That's the first k nearest neighbors regressor we built. And then in purple, we have a lower variance model, a higher bias model that requires the model to look at 7 nearest neighbors when making predictions. And you'll see that this one is the least sort of wiggly out of the 3 models. And in general, as we move this number of nearest neighbors higher and higher, we're going to end up with a less flexible model. All right, so here's a recap on regression. This has been really just a crash course to say, hey, there are a bunch of different types of regression model out there. Those different types of models behave differently, and they're structured differently. They make different predictions, even given the same data. And that's because these different model classes make different assumptions about the data. Some of them make assumptions about probability distributions. Some of them make assumptions about distance. And so different classes are more or less suited to different applications. We've got to be careful about which model class we choose for a given application, or at least we've got to be really good about assessing different models. So what we'll do most often is we'll build and explore a bunch of different model classes for a given application, and then we'll score those model classes against one another. We'll kind of have them compete to determine which model class is best suited to our application. So before we move forward, here's just a gallery of the regression models that we considered. So we looked at, in this first row of plots, linear regression models. So we had a straight line linear regression model and a curvy linear regression model. We looked at decision tree regressors. These were more flexible than the linear regression models. They were structured in the models actually are structured in the form of yes or no questions. And so we end up with a bunch of kind of flat plateaus that make predictions here, rather than kind of a continuous set of predictions, a continuous change in the predicted values. We looked at a support vector regressor. This one, again, I'm showing you not just the support vector regressor, but also the original linear straight line linear regression model. These ended up looking quite similar to one another in this run of the notebook. But if we generated new data, we may end up with less similar models there. And we looked at nearest neighbor models as well. These models make the assumption that observations are most like those observations that are closest by. And we saw that the fewer the neighbors you were consulting in making a prediction, the more flexible the model was, the higher variance it was. And then the more neighbors you were consulting, the less flexible it was, the lower variance the model is, and the less likely the model is to overfit the data. What's important to note again is that there's no one model class that's dominant across all applications. And for this reason, it's going to be important for us to try multiple different model classes in a given application or given scenario to try to determine or uncover which model class is best suited to making predictions on that data. So now let's move to classifiers. I just want to show you a classification application and some of the different model classes that are appropriate there. So what we're going to do is we're going to build a new data set. This data set is going to have two predictors, x1 and x2. Don't worry so much about the code here. I'm essentially generating some random numbers between 0 and 40, then some more random numbers between 30 and 70, and then a third set that are between 60 and 70. So these are going to end up being like 3 clusters of points. I'm going to do the same for x2. So some random numbers between 0 and 40, some random numbers between 30 and 70, and then some more between 0 and 40 again. Then I'm going to generate color classes for each of these. So for the first sets where I had the x1 coordinate between 0 and 40 and the x2 coordinate between 0 and 40, I'm going to call those red points. Then for the second set, where my x1 points were between 30 and 70, and the x2 points were also between 30 and 70, I'm going to call those blue. And then for the remainder of the points, we'll go back to red. We'll build out a data frame to organize these observations, and then let's take a look at what the data frame looks like. So I have an x1 coordinate, an x2 coordinate, and then a color. And if we build a scatter plot of this, we can see the data that we're working with. So I've got this lower left kind of area in my plot where x1 is small, x2 is small, and those points are red. Then remember the second collection where x1 was kind of in the middle, 30 to 70, and x2 was as high as we allowed, 30 to 70. Those points were blue. So here we're seeing that they're blue. And then that third set of points where x1 is very large and x2 is back to being small, those are red again. And so our goal here is essentially to separate the red points from the blue points. In some sense, classification can really be thought of as just drawing fences. The more wiggly your fence is allowed to be, the more flexible your model. Remember, more flexible models are associated with higher variance and higher likelihood of overfitting. So we kind of want a happy medium between accurately fitting the training data, but not being too flexible, not risking overfitting by too much. So let's get on with the model building. We'll start with a tree-based model. Actually, all of the model classes here we've seen before in the regression setting. So decision tree classifier looks a lot like a decision tree regressor. It's going to ask a series of yes or no questions. We're going to build an unconstrained decision tree classifier, and then one that is constrained where we're setting the maximum depth to 2. So we'll create instances of those, then we'll fit them on the training data. Again, our training data now contains both an x1 variable and an x2 coordinate, and we're trying to predict the color as the class or category. And the same thing for the constrained tree. So now that we've fit those, what I'm going to do is I'm going to try to draw the model kind of in the background here. So these models are fences rather than functions. What I'm going to do is create a grid of points. So this is just going to cover the background and allow us to plot the model kind of in the background. We're going to make predictions using our model on that grid of points, and then we're going to plot the results. So here we can see that the constrained tree and unconstrained tree are actually identical. What I'm going to do is I'm going to cheat a little bit and I'm going to regenerate our data. This is kind of a boring data set. This one looks a little bit better. You see the blue and red points are kind of intermingling. Let's see. Now, yeah, so now we can see a little bit more detail in the unconstrained tree. So the unconstrained tree is chosen to kind of carve out this little rectangle for blue observations, where the constrained tree said, no, that's not a question that's worth asking. It's going to put me at risk of overfitting. The unconstrained tree also looks like it carved out this little area to make sure that that blue point was classified as blue. And so this is more flexible in the unconstrained tree case. The fence that we've drawn is more wiggly. Rather than in the constrained tree, it looks like we've just got one kind of flat straight line across, saying that if the x2 coordinate is small, I think that the point is going to be red. If the x2 coordinate is large, I think it's going to be blue. All right, let's take a look at the support vector classifier. So again, like trees, support vector machines have both the ability to work in regression settings and classification settings. As a reminder, these are distance-based models, and so categorical predictors are not well suited to these things. Let's generate a couple of support vector classifiers. We're going to make one that's linear, and then we're going to do one that's much more flexible. It uses a radial basis function. So there's a lot of linear algebra behind here. Again, this is a business class, so we're not going to talk about the linear algebra. But the linear kernel is going to force us to have a more rigid kind of straight line separators. And the radial basis function for a kernel is going to allow us to build kind of an oval or a much more rounded fence. So we're going to take these classifiers that we've created instances of, and we're going to fit them to our data. We'll then generate predictions on our grid, and then we'll plot the results. Again, we're interested in kind of what the fences here look like. And so the support vector classifier here looks quite a bit like the decision tree. It's kind of identified that observations with small x1 coordinate are probably red. Small x2 coordinate are probably red, and large x2 coordinate are probably blue. It looks like the fence, though, was drawn at a lower height, at a lower x2 value for the tree case, and a higher x2 value for the support vector classifier case. And then with the radial basis classifier, using a radial kernel, we're allowed to not just draw kind of a straight line rigid fence, we're allowed to draw regions and closed regions. This is kind of interesting because we're capturing many more of the blue points accurately. But now this model would suggest that, well, if my x2 point coordinate is large enough, say 100 or more, well, we'll predict that that is going to be a red observation, where we have no data points, no training observations to justify that. Kind of interesting. Okay. And so one last model class before we close this out, let's take a look at k nearest neighbors classifiers. Again, similar to the previous two examples, so tree-based models and support vector machines, k nearest neighbors can be fit to regression and classification tasks. Similar to the k nearest neighbors regressor, a k-nearest neighbors classifier is going to assume that any new record is most like its closest neighbors. So the classifier is just going to look at the number of nearest neighbors we specify. It's going to allow those nearest neighbors to vote on an assigned class, and then those votes are going to be aggregated and a prediction will be made by the classifier. So one way to aggregate is just to say majority rules. So if I'm looking at a k-nearest neighbors classifier with 3 nearest neighbors voting, and for a new record, I have 2 close by neighbors who are red and 1 close by neighbor who is blue. Well, now I have 2 votes red, 1 vote blue, so the new observation would be classified as red. Okay, so let's compare 3 k-nearest neighbors classifiers. We'll have one with k as 1 nearest neighbor. Again, that 1 neighbor is going to have all of the voting power. So this is going to be a very flexible model. One with k is 3 nearest neighbors, so kind of a middle ground. And then a final one with 7 nearest neighbors voting. Here, because so many neighbors are voting, each individual data point has less influence over the prediction made by the model. All right, so again, we're going to import the k-nearest neighbors classifier from the neighbors submodule of scikit-learn. We're going to create instances of our classifiers. So KNN1 CLF is a k-neighbors classifier with number of neighbors equal to 1. Then we have a k-nearest neighbors classifier looking at 3 nearest neighbors, and then 1 more looking at 7 nearest neighbors. So we've created instances of all of those objects, but they haven't been fit yet. So next thing we'll do is we'll fit them to our data. So the models are going to get to look at the X1 and X2 columns of our data frame and try to predict the value that they see in the color column. That's the same case for all 3 of our k-nearest neighbors classifiers. The difference is going to be here, where we've defined the number of neighbors that they're each going to look at when making their predictions. Then, once the models are fit, we'll make predictions on that grid and we'll produce the plot. So again, we're using the grid as kind of the background to discover what the fences these models are drawing is going to be. And so on the left, we have the k-nearest neighbors model with 7 voting neighbors. So here, each neighbor has kind of a little bit of influence in determining what color the background here is going to be assigned to. A little bit of influence. Each one has 1/7 of the decision-making power, right? 1 out of 7 votes. This results in boundaries that are mostly kind of straight lines or straighter lines. Once I decrease the number of voting neighbors, now each individual voting neighbor, so now for a new data point, say here, I'm going to identify the 3 closest neighbors to that observation or record or region in space. And I'm going to say, hey, you 3 nearest neighbors, vote. Now each individual observation has 1/3 of the decision-making power. So each observation is more powerful and more influential. And that results in more flexible boundaries. And so you'll see kind of red has notched out this area. And then in the case of 1 voting neighbor, so there's only 1 nearest neighbor voting on any prediction. And so each individual data point is very, very influential on the shape of the model. You even see here, this blue data point has kind of carved out a little island for itself in the red region. And I think that this is definitely evidence of a model that's overfitting. All right, so again, we've seen a bunch of different classes of model in the classification case. So that misspelling is going to bother me, so we'll fix it. Yeah, so the different models result in different decision boundaries. The model the class of model we choose can drastically impact those boundaries and the resulting model performance. And so because of that, we're going to often compare multiple model classes against one another in any application, just like in the regression case. And just to close this out, we'll show a gallery of our constructed classifiers below. So here's all of our classifiers and their performance on the data that we've trained them on. We didn't use any test data throughout this notebook. So we haven't really assessed the quality of the fits on these. We're just interested in the different shapes of decision boundary, the different types of model, and the resulting predictions that we can get out of those model types. So again, the kind of the big punchline here is that the class of model you choose can drastically impact the type of predictions you're making and the performance you should expect out of that model. So here we had the constrained decision tree, an unconstrained decision tree that was kind of allowed to notch out more areas to make sure that it fit all of the training observations. But our goal, remember, is not to fit training data necessarily, it's to fit new data. So we want models that are going to generalize. So fitting the training data isn't the primary objective. We had a support vector classifier with a linear kernel versus a radial kernel. The radial kernel was allowed to kind of grow an island for the blue observations. And then we had the nearest neighbors classifiers with 7 voting neighbors, 3 voting neighbors, and 1 voting neighbor. Again, the lower the number of voting neighbors, the more flexible model you're getting. The higher the number of voting neighbors, the more rigid a model you're getting, because each individual training data point has less power in determining the ultimate prediction being made. All right, so I think that's it for now. This has been just a discussion on different model classes. What I hope you're getting out of this discussion is that there are more than just linear regression or more than just a decision tree. And when we make a choice about a model class, that choice is going to impact how well our model performs or how strong our predictions are. And so it's important to consider a variety of model classes in any given modeling project or predictive analytics project. So we'll leave it here for now. We'll talk more about truly assessing models mathematically in a later notebook. All right, thanks everyone. I hope this has been helpful, and I'll talk to you next time.